right, good morning and welcome to the second half of the course. Now, the second half is mainly concerned with geometry and related concepts, and for the most part, it'll actually have a slightly different format and a different look to it. Like today, for example, we'll just have some slides and it depends on the topic. But regardless, it's all geometry related. Right. So the first is an introduction. Basic concepts. What do we mean when we talk about a polygon? Those are things that we have to get comfortable with, and some of it you will be already. Some of it will be very familiar, but maybe there's something that isn't, and I can't assume that everything is familiar, so we have to start here. But uh, throughout, many of these things will be familiar to some people. Okay, let me just see if the screen looks okay. Yeah, it looks okay. I'll just leave it like that. So, when it comes to geometry, we really have points and lines, and those things could overlap and intersect and create shapes, essentially. Now, we won't get too fancy with it and be all formal. We'll be somewhere in the middle. So usually we name points when we have to sort of write an explanation or read instructions for how to make shapes and do stuff. The points are often named with capital letters. Then 2 points can be connected with a line. We'll call that a line segment, ending at the points sometimes. And that can be represented, that line segment, by just indicating the 2 points that it goes between. And maybe a line over top to indicate that's a line, not just two separate points. Sometimes we extend the line past one or both points. Some people call that a ray. I don't really care for that word at our level. We want to keep things as simple as possible, right? We don't want to introduce words unnecessarily. We can easily just say the line through points, and then the diagram clarifies that it just extends. Sometimes we need that. But regardless, it has a very similar representation, maybe with an arrow. Even if you don't use an arrow for our level, it's not going to be the end of the world. Regardless, we need the 2 points to specify a line uniquely, whether it ends at the points or extend through them. Still a unique line, essentially. Then we have a polygon. Now we'll elaborate on that in a second. But often the corner points of the polygon are points, whether they're big black dots or not. They can be labeled with capital letters, and then the polygon is specified by just listing all of those points in sequence, starting wherever you want. Okay, so these things might come up now and then, not every time, and the more formal and proper you want to be, of course, then the notation becomes super important. We're not going to go that far, but it is there in the background. So we're going to start our introduction with the concept of a polygon. Polygon, the word comes from poly meaning many and gon meaning angle. Now our first goal, we'll have many goals. Our first goal for today is to understand the names of different polygons, be able to draw examples of them, and identify which polygon is which. Now, just to make things a little bit more interesting, these things were sort of developed over time without a lot of future forethought, I guess, about where this could go. As people discovered polygons and shapes, it started with a simple triangle. And they didn't think oh, where could this go one day? Of course, they don't know. So they were naming things as they saw fit at the time. So often you see different prefixes, different little pieces making up the name of a polygon. Sometimes it's the word gone, sometimes it's angle, sometimes it's lateral, meaning sides. But in general, eventually things got bigger than a triangle and a rectangle with many more sides to the shape. And then eventually they decided, okay, it's silly to just make new names when there is no limit to how many sides or corner points this shape can have. I can have many, infinitely many. So at some point, we're going to say, and we're going to call it an n-gon, n referring to the number of sides and the number of angles. Now just take note here for our little example, and we'll see more examples. The number of sides in the polygon is the same as the number of corner points or the number of angles. They're the same. In this case, I have 4 sides, 4 corner points. They're always going to match. So an n-gon, the n is just going to refer to how many of them there are. So 10-gon is just a sort of general standard name for a 10-sided polygon. But you can have 100-gon, and so on and so on. Because after a while, the names became a little too much. But for the smaller sized polygons, we do have these names that we have to know and understand because we don't have to teach them. But let's clarify what a polygon technically is. There's a couple of requirements. A polygon is a closed planar figure. What does that mean? Well, I'm drawing a shape. I'm drawing it on a two-dimensional surface on the plane, on your screen, on your paper. Call that a planar figure. And it has to be closed, meaning I can't have an open gap. And we're going to see examples in a second. And it's made up of line segments. That's a line segment, straight line segments. Joined end to end with no crossings, no reuse of endpoints. So let's have some examples we can think about. And there are some in the book as well. I don't think they overlap. We'll just do them all. So in A, you see there's a gap there. The line segments don't join end to end. These last two don't, the top two don't join together. Not a polygon. In B, it's not a polygon because those side lines are not line segments. Line segments are straight lines between 2 points. Not a polygon in B. In C, it's not a polygon. For one, you can maybe see it as 4 points, the 2 left ones and the 2 right ones, and the line segments in the middle, they cross each other, and that's not allowed. No crossing, no reuse of endpoints. Even if you see that middle one as a new endpoint, a new point, well, now it's used too many times. Can't do that. Can't have any sort of visual crossing. That's just a fancier shape. And our introduction is going to start with the simplest shapes that have the most structure that we can sort of build on and understand. And these are too fancy. So polygons are the starting point. D as well, many crossings and many things here that make it not a polygon. And E, you have a crossing there. You have a reuse of points for more than just 2 line segments, not a polygon. Let's just go and have a look here at, okay, not yet, because in exercise 9.1, I want to identify if the following shapes are polygons or not, and name them. We haven't done the naming yet, so we'll come back to 9.1 in a second. So now, let's talk about the names. And this is where things get fun, but also not completely unfamiliar. These things should be fairly familiar. We have triangles, so we can group the polygons according to the number of sides, number of angles, number of corner points, also called vertices. Whatever you want to call them. In a triangle, all of those things are 3. In a quadrilateral, all of those things are 4. 4-sided polygons. And then we can increase the number of sides to pentagons, to hexagons, hexa meaning 6, heptagons, 7-sided. You see these weird ones, this crown shape over here? It doesn't have to be a roundish polygon, sort of rounded as much as possible. It can have sort of indentations and all kinds of things. The requirement to be a polygon is still there. Number of sides, line segments joined end to end and closed. Hepta meaning 7. Octagon, octagon meaning 8-sided or 8 angles. Nonagon, 9. And a decagon, deca meaning 10. The star here, 10 sides, satisfies the polygon requirement, though in truth, when we think about a polygon and have to draw our own example, we do tend to think about a round shape, roundish, or a bulging shape. Though this guy on the left here, also a decagon. Doesn't have to be that perfect, roundish, balanced, symmetrical shape to qualify as a polygon. So now let's go to this exercise 9.1. Zoom in a touch more. So number 1, yes, it's a polygon. It is a pentagon. You just count the number of sides. And because they're all straight lines, they're easy to count and easy to identify. You can count the corner points, you can count the vertices. This is going to be the same number every time. So a polygon has that nice simple structure. As simple as we can really make it. Then on number 2, we have a polygon. It's a triangle. And we're going to classify things like special types of triangles and so on in a second. So now it's just triangle, yay or nay. Yay, triangle. Over here at number 3, I have 1, 2, 3, 4, 5, 6, 7 sides. Satisfies the polygon requirement. It is a heptagon. Number 4, no, I cheated. I copied it from the other slides. It is not a polygon. I'm crossing or I'm reusing an endpoint, whichever way you want to see that guy. Not allowed. And number 5, I have a quadrilateral. Quadrilateral. You can say a fourgon, but for the small ones, they have their own names. It's really when it gets bigger. Then we start using the n-gon format. For these small ones, it has its own name, quadrilateral. And then number 6, so let's count the sides here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is a decagon, even though it doesn't look like it. You want to call it a star? Star is not technically the name of a polygon. Alrighty. Hopefully everything is good and fairly familiar so far. Maybe not everyone works with heptagons often, but most of these words, most of these names are somewhat familiar. This is just our introduction, but a very, very important step that I don't want to skip. Now, we have special kinds of polygons where we don't necessarily want to open it up to just anything here. Maybe that's a little too big. Look at this guy. Almost looks like a face. And that's the mouth. Put an eye right there. Anyway, we don't want to open it up too much, even though we do have some structure. Let's get some more structure. So an equiangular polygon is a polygon whose angles are all the same size. An equilateral polygon is a polygon whose sides all have the same length. So, and a regular polygon, let me just finish it. A regular polygon is a polygon who's both of those. Equiangular, all the same angles, and equilateral, all the same side lengths. So just visually, if we look at these guys, this triangle over here might be, I have to measure it to be sure, looks like an equilateral triangle. All the same sides. And in this case, it also has all the same angles, so it's also equiangular. So this would be a regular triangle because it's both. Right? Let's clarify here. Equiangular is a requirement just on the angles. Equilateral is a requirement just on the side lengths. If I get both, which isn't always going to be the case, I call it a regular polygon. So a regular polygon has the most structure sort of possible that we're going to look at. So I can see here, this guy over here, this quadrilateral, has all the same angles. So that will be an equiangular quadrilateral. Yes, we will later call it a rectangle. This guy over here has the same property, but also the same side lengths. So that's an equilateral quadrilateral. Ooh, that's a mouthful. That is a mouthful. But for example, for example here, a square can also be called a regular quadrilateral because it has all angles the same and all sides the same. But who wants to say that every time? So it has, some of these have their own names, like the square, not many. And then we can go and examine bigger and bigger ones. This decagon star looking shape has all the same side lengths. So it's equilateral. It's an equilateral decagon. But the angles are not all the same. See, this is a small little angle here. That's a bigger interior angle. They're not all the same. So it's not equiangular. It is not a regular decagon. So I want to get used to those words. Some of it you might feel more familiar with. Maybe equilateral feels fairly familiar. Equiangular is not used as much. Regular is arguably the most important word here. Regular. Okay, so let me just briefly talk about angles. We're not going to worry about them too much until much, much later. But we have different kinds of angles. And when we talk about the angles of a polygon, we talk about the interior angles inside the shape. We have our familiar right angle, 90-degree angle, or square angle, or whatever you want to call it, right angle. Then we have angles that are less than 90 degrees, smaller, we'll call them acute angles. Then we have angles that are bigger, obtuse angles. And then technically when it's just perfectly flat or 180 degrees, sometimes we call that a straight angle. But the more important words are acute, right, and obtuse. And we usually measure it in degrees when we want to just have an intuitive feel for these angles. It's a nice intuitive measure of an angle. All right. So now let's go in order. Just focus on the triangles and classify those a little bit more precisely and then build up from there. We're really only going to focus on the triangles and the quadrilaterals. And after that, with more sides, it opens up a little bit too much and it's either regular or not. But with the triangles and quadrilaterals, they're used more often than anything else in elementary school, so we dig a little deeper into classifying them. All right. Classifying triangles. A lot of this will be familiar, but these are words that you will use in elementary school, so we have to know them. An acute triangle has each angle measuring less than 90 degrees. Let's go look for an acute triangle. That is an acute triangle. All angles are acute angles. That one is as well. This one, for example, is not. Because, yes, those two angles are acute. That one is bigger than 90 degrees, this top one. And we call it an obtuse triangle if one of the excuse me, one of the angles is greater than 90 degrees. Can't all be greater, right? Because I have to close it again. Where is my drawing? I didn't open it. Let me open some drawing stuff here. Open the drawing program. So one observation I can make is that an acute triangle can have only one not acute, sorry. Oopsie, the other one. Obtuse. Only one obtuse angle. Because if I try and draw one with multiple, let's suppose we need one angle, right? Let's make a big one. Like that. Now, I need to connect them. I only have one more side to close this polygon. And if I make this one a big angle, bigger than a right angle again, now I'm going off somewhere else and it's open. Open. So that's not allowed. I can't do it. It's impossible because a triangle has only 3 sides. So I can make little observations like that. And a right triangle or a right angled triangle has one angle exactly 90 degrees. We'll revisit those a little bit later. Then if we look at the sides of the triangle, we can have some sides being the same, sometimes some sides not being the same. If all of the sides are different, we call it a scalene triangle. Let's see if we can find one in our examples. This guy, the second one in the list, that's a scalene triangle. All sides are different. There could be a property on the angles. It could be a right angle triangle. But with scalene, I'm referring to the side lengths. An isosceles triangle has 2 sides the same length. So this guy on the left here is an isosceles triangle, or at least looks like it. I should technically measure it to be sure, but it does look like it. Isosceles triangle, those 2 sides are the same, but the other guy is a little short. He is not the same length. And then when I have all 3 sides the same length, we call it an equilateral triangle, of course, because equilateral means all the same size, the side lengths. So it should be called an equilateral triangle. Now, in the case of a triangle, like we said, an equilateral triangle is, let's say this one, looks pretty close. Equilateral triangle is also going to have all the angles, all the interior angles the same, and it'll also be equiangular, and therefore we can also call it a regular triangle. Now, I'll note here that to be actually precise when you draw a polygon of any kind, if I want to draw an isosceles triangle, I can't just make it look, because my drawing is not going to be precise, right? So what we often do is we put little lines through the sides that are equal. And if I don't put lines through it, then it can be assumed that it's not equal, or I'm not trying to I would have to verify it by measuring it. And because I'm just sort of freehanding this, measuring it is not going to be perfect, right? That side is probably technically a little shorter. But when I indicate it with 2 little lines, they are now, whether they are measuring perfectly or not, they are now equal. And that is an isosceles triangle. All right. So when I want to draw an equilateral triangle, for example, because I'm doing it by hand, it's not going to be perfect. I try, That's close, but if you measure it, I'm sure it's not. I verify that that was my intention by putting these little lines through it and essentially stating these are the same length. If they're not, maybe I have a right angle triangle, maybe like that. Of course, my drawing is not going to be perfect, right? I try my best, but maybe this isn't perfectly 90 degrees because I was freehanding it. I put a little square in there to emphasize that my intention was to make that 90 degrees. That, for all intents and purposes, that is a right angle. But maybe these sides aren't the same, right? Maybe that side needs to be different than that side, which is different than that side. So that should be 2 lines. So the number of little lines, if the number of little lines are different, then that indicates that the length of those sides are not the same. So this has only 1 line, this has 2 little lines, this has 3 little lines. They're not the same length. Sometimes visually it's obvious, but sometimes it's so close that I need to have these little indicators that what the length is supposed to be, because I'm just freehanding this. Okay. So my first step certainly is to be able to draw each of these kinds of triangles and understand what these names mean. So something to think about. Let me just check if that's on the screen. Bottom there. Why is an equilateral triangle a special kind of isosceles triangle? An equilateral triangle, I have to understand what that means. An equilateral triangle requires that all the sides are the same. All the sides are the same length. So if I look at this guy, this is equilateral, where my arrow is. So necessarily, 2 of the sides will be the same. This is also an isosceles triangle. Don't read more than there is. An isosceles triangle doesn't require that only 2 sides be the same length and the other one not. It just says 2 or more sides should be the same length. Maybe just 2, but maybe all 3. So an equilateral triangle is a special kind of isosceles triangle. Sometimes I can put a little extra line through there. See, that's bottom one's not the same length. Isosceles triangle, not equilateral. But sometimes they are all the same length. Then it's an isosceles triangle, but a more specific one called an equilateral or a regular triangle. Okay, so we want to be comfortable. Whoopsie, what did I just do? No, get back here. We want to be comfortable. Actually, I'm maximizing that. Be comfortable with the different names and classifications for triangles. That is the first goal. And if it takes a while, it takes a while. There's no sidestepping this. This is guaranteed in the elementary school curriculum. Absolutely. Can't sidestep this. It's must-know things. When it comes to quadrilaterals, it gets even more fun. But that'll be the last one we really classify in this much detail. So it's only the triangles and the quadrilaterals that will go into that much detail on. Quadrilaterals. We have a whole bunch. And some are special cases of others, and so on. So in order to clarify this a little bit, I'll draw sort of a hierarchy, if you will, connecting these. And what makes it a little bit more confusing, unfortunately, is there isn't just one definition for these special kinds of 4-sided polygons, these quadrilaterals, unfortunately. I'll give you my sort of intuitive, comfortable way of understanding and remembering the links between these. But when you look at the slides that I'll show later, when you look at other books, there are many words you can use to explain some of these. So let's start with our quadrilaterals. Oops, quadrilaterals. Among these four-sided polygons, there's more structure possible, and they might have their own names. So first up, we'll split it into two kinds. We want to now be more specific. That the quadrilateral, remember, just as long as it's a polygon with four sides, it's a quadrilateral. But some of them could be a little bit strange. And maybe that's too general. So we're going to make it a little bit more specific by saying, let's not allow anything, but let's require that two opposite sides should be parallel. Now, I know we have not defined the concept of being parallel, but we'll have to wait for that. And it's okay because many of us have a concept of what parallel is. Like train tracks, right? The distance between them stay the same forever. So it's a little bit more structure because in general, some quadrilaterals won't have that special property, right? But some of them will. And if it does, only a pair of opposite sides is required. Could be more, but is not necessary. So I'm not writing these out in words. You can rewatch the video and write it out if you want to. A trapezoid is a quadrilateral that has at least one pair of opposite sides parallel. Then we can say, okay, that's nice. I like it. What else could we do to the general family of quadrilaterals? Well, we can, instead of focusing on opposite sides, we can focus on opposite angles. That's a little bit vague, unfortunately, to get us anywhere close. So they decided on, oops, not eraser mode. Where am I now? I want the line. They decided on what we call a kite, which has two adjacent sides the same length, like that. So that now indicates same length, as well as the other two adjacent sides the same length. My straight line tool doesn't always want to play with me perfectly. So I'll indicate that those two are the same length, right? So sort of a side effect of this, which I guess is what they really wanted to aim for, is that the opposite angles are the same. But if I just require that, it opens me up to a little bit too much. So the other kind of initial classification in the quadrilaterals is where a pair of adjacent sides should be equal length, and then the other pair, because I have four, should be equal length as well. Now again, they could all be the same length. I don't require that. That is a more specific kite. So we can go lower into this and require more specific structure than just these two. But that's certainly a first step. Then I can say, let us split the trapezoid into two more specific kinds of trapezoids. First one is not that common, but sometimes people mention it. It's certainly the least common of all of these that I'll draw. Isosceles trapezoid. Now I understand what an isosceles triangle is. So an isosceles trapezoid is a trapezoid which has these other two sides the same length. So it's not, the top one is not isosceles, but, and I'll try and draw it as precisely as possible. That is a little closer, so I'll fix, oh no, erase, my line was a little too long. And now I'm indicating, okay, those, oopsie, I'm in eraser mode. Those are the parallel sides, and those two are equal. I could have more sides equal and more sides parallel, of course, but one tighter restriction I can make on a trapezoid is that these other guys have to be the same length. So there's a little bit more structure, a little less wiggle room now. And the one you should be more familiar with, whoopsie, is a parallelogram, where I require the trapezoid. It's a special kind of trapezoid. The trapezoid said only one pair of opposite sides needs to be parallel. A parallelogram says no, both pairs of opposite sides must be parallel. Just fix my drawing here a little bit and indicate those are parallel. Two arrows, those are parallel. Now there's a lot of side effects from this requirement that the opposite sides are equal as well, equal length, because you'd have to prove it a little bit more formally, but there's a lot more structure. As soon as I require that both sides are parallel, now the structure is quite a lot. All right, so a parallelogram is a special kind of trapezoid because it requires both pairs of opposite sides to be parallel. Then I can go further with my parallelogram and require a little bit more structure there. First of all, I can require that the parallelogram also has the same angle, interior angles, and then I'll get a rectangle. I have a rectangle tool. Perfect. So now I have my parallelogram, but I also require the same angles everywhere. And because they're all the same, because I have 4 of them, they'll all be 90 degrees. All right. So notice that a rectangle is also an isosceles trapezoid because the rectangle has opposite sides the same. I can technically make a line there. These two aren't quite on the same level, but it's okay. So the parallelogram, I'll put these in brackets. It's certainly not very important for us. The parallelogram path is more important. So a parallelogram requires both pairs of sides be parallel, make the angles the same, and I get a rectangle. Then I can skip the angle requirement and say all the sides should be the same. The angles don't have to be the same. All the sides should be the same. Of course, I still have this parallel aspect to them, right? Just fix my little gap here. So there's still a parallelogram, special kind of parallelogram, that all the sides are the same. And then we get our rhombus. So different ways to go from the parallelogram. These two, the rectangle and the rhombus, come together in the square. So I can get to a square in multiple ways. Let me just draw the square. I can get to a square in multiple ways. I can go via a rectangle and then say it's a rectangle with all sides being equal, because the rectangle has fixed the angles already. Or I can go via the rhombus, which has all the sides equal already, and say that a square is a rhombus with all angles being the same. In each path, I get the square. So the rectangle and the rhombus overlap in the square. A square is a special rectangle, a square is a special rhombus. Another observation I can make, let me zoom out a touch. Ooh, not that much. Is that the rhombus, because it has all equal sides, every pair of adjacent, of connected sides are equal, it is a special kind of kite as well. I'm going to draw a line here, but we'll see. I won't, but a parallelogram is necessarily isosceles, right? Because the sides, the opposite sides are the same. But in some cases, which is why I put this in brackets, some people view an isosceles trapezoid as not a parallelogram, just to make your life difficult. So I like to include it here, but it's okay. I guess we should put arrows, right? Specializing this way, this way, this way, this way, this way, down. So ones down the arrow are more special or more specific types of further up. So the most people struggle with, in my experience, is the kite. The kite. It is a little different. Look, it's sort of on the side here. It's not a part of this nice long chain. Trapezoid, parallelogram, rectangle, rhombus, square. That's the familiar chain, right? Kite is sort of on the side, and then it links back up when we get to rhombus. But it's very useful if I can just have a big picture of how these quadrilaterals relate to each other and sit in relation to each other. And I can use that understanding to write a definition for what the shape is. Now, if you pay attention and rewatch the video, the way I define these isn't the only way. I'll put other ways up here, other words used to define these. Some of them are the same as mine, some of them not necessarily. Making it a little bit more confusing, admittedly, that there isn't one specific definition of a parallelogram, of a rectangle, of a square. But just pick one that you find comfortable, that fits in this hierarchy, and I think you'll be okay. So it's beneficial, just like we organize animals into different categories and subcategories and subcategories. Having these shapes sort of visually connected helps my understanding a lot. But we stop there with that much classification. When it gets bigger, pentagon, hexagon, and so on, we are happy with, where is it now? Equiangular, equilateral, regular. Nothing more specific than that. And we'll find later on, regular is the most important one. Okay, so that's basically it. I have a little bit extra in our last few minutes, but regardless, there's all of that is in the book. Very, 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 very important are all these problems. I have a lot of them so that you have a lot of practice. Don't be confused with the numbering of 9.2. These are separate questions. 1 and B are separate. They're just a mix of typos. Okay. So even though our formality of geometry is going to be a little bit in the background, the next topic is going to be there, but we don't necessarily write our logical arguments out because we don't have time, unfortunately, to go that proper of a route. It is important to understand the importance of geometry as a subject, that all these things had to be specifically thought through, logically argued, because our perception of lines and shapes can lead us to weird conclusions. Like in A, the positioning of these lines make the vertical ones seem longer, when in fact they're the same length. The placement of these arrows backwards and forwards and whatever, or flipped around, make the PQ line seem longer than the RS line, but they're the same. And then because we're representing things on a two-dimensional surface, whenever we try and represent three-dimensional shapes on a two-dimensional surface, we can get weird things like this, the impossible triangle, where if you look at this for long enough, it gets worse. Like here, this is the outside of the triangle, which then becomes the inside, which then becomes the outside. The longer you stare at this, the worse it gets. It's impossible. Can't be done. But the importance is therefore to not rely on our perception of lines and shapes and objects, but have clear arguments for properties of these shapes. However, in Australia somewhere, I think, people actually built the impossible triangle as an optical illusion. If you stand in the right place, it's actually going to look like this top left one. It's not a triangle at all. But if you just stand at the right place, the two will seemingly sort of overlap there and make one connected triangular shape, which we know is impossible. So on a two-dimensional picture, it can present an illusion where the three-dimensional reality is quite different. Let me go to the next one here. Oh, this one is flipped around. Hold on. And you have this impossible staircase where the stairs go up and up and up and up and up, and they never go down. Just go up in a circle. How is that possible? We're exploiting the two-dimensional, the difference between 2 dimensions and 3 dimensions. M.C. Escher is quite a famous artist that really exploited this optical illusion aspect. And here's the impossible staircase again. People just keep going up and up in the same way, even though they go in a circle. This waterfall one, where the water comes down and then flows up and comes down again. Something I know realistically is impossible, yet on a two-dimensional picture looks quite believable. If you look at these lines, I need to just zoom out a touch. Look at these lines, they do not appear parallel at all. And it's the presence of these slanted lines that make them all wobbly. If I remove the slanted lines, the vertical lines are exactly the same. Parallel, not parallel. Parallel, not parallel. I cannot trust my perception of geometric shapes. Here, these vertical lines or the columns do not seem parallel at all. But they are. Parallel, not parallel. Parallel, not parallel. And someone actually went to build this, where it looks a very poorly designed building. But it's simply an optical illusion and everything is straight and parallel and perfectly designed. Some things you might have seen, the presence of these lines make the left guy appear larger than the other guy, but it's the same guy. And the positioning of the wall with the bulls make the brown one seem bigger than the black one, but they're the same bull. So it was very important initially to, we're almost done, to not rely on our perception of what things look like because it can so easily be manipulated. That long ago, where's my page now? There we go. Euclid sort of started this view of systematically, logically building up properties of shapes and geometry by just relying on 5 postulates that everyone can agree on, everyone believes, and everything else has to be logical arguments and logical conclusions based on these 5 and not what things look like, because what it looks like might not be reality. So his first postulate, now this is his original words, I'll rephrase this, is that between any 2 points there's a unique straight line. And if you extend that line, you can only do it in one way. There's only one straight line, regardless of how far you extend it. And if you give me a point and a specific radius, there is only one circle that you can draw. And that we will use in the next topic a lot. Sort of these things are in the background, but technically everything we'll do, even though superficial, has been logically proven in the background. All right angles are the same. It's all the same size. And this one's a little wordy, but you can read this afterwards. I'll just describe it. Where is my drawing? I'll just describe it. Can I go to the first page? Below here. Essentially what it says, if I have oh no, what did I just do? There we go. If I have a line, boom, there's my line. Let's make it vertical, make it nice. And I look at 2 lines intersecting this. If the angle that those 2 lines make with this vertical given line is less than 90 degrees, might not be the same, right? But it's acute, then eventually these lines will intersect. Intersection is inevitable. Or another way of saying it, then from this, the property of parallel lines come out of this postulate. That as soon as I don't have 2 90-degree angles here, these are not parallel and they will intersect eventually. Now, I would love to dig deeper into this, but it takes too long. We have other things, more elementary school focused to focus on, to discuss. But these things are always in the background. A structured, proper, logical foundation of all the geometric properties that we'll see. All right, sorry for going a little over the time, but that was our introduction. Absolutely make sure you can do each one of these problems. They're must-do problems. All right. Are there any questions at this stage? All right, then we will pick things up tomorrow with a new section, but of course related to the geometry subject. Until